right. So mallocs. In PA1, as we built our linked list, when you wanted to add a new node, what did you do? You called a get node function that you wrote. And get node looked through your array and said, hey, here's, the fifth element in the array that's not being used because the valid bit was set to 0. And so it sets the valid bit to say this is in use, and it returned the value 5. And then your add function that called getNode says, hey, I can store my new node in location 5 in this array. Alright? That's what malloc's doing for us in PA2, but instead of calling our own function and looking for space in an array, we call the system function, which looks for space in effectively a big array that the system keeps track of, called the heap. And so you want to call malloc primarily in your add function, right? Every time that you want to create a new node, at the place that you would have called getNode in PA1, you're going to call malloc. And you're going to call it with a size of struct node. And it should return something different from null, and that will be the address in memory where you store your new node. Now the one other place you're going to want to call malloc is in your init function, and this is where init differs from PA1's init, because your sentinel in your main program is going to be a pointer to a struct node, and so init's going to have to allocate an initial block and then return the address of that with the next field set to null. So init returns a struct node star. I am upside down and backwards. Upside down Monday. It's on my list to fix that. But I have a few things on my list. Alright, so init returns a struct node. And, it's really a two-line function. So inside init, call malloc, give it the size of a struct node. It'll return a pointer to a struct node, which I just stored in a variable called s, and then just return that. And in your main program, you have a sentinel declared. And to give it a value, just call init. Save the return value. Alright, so that's the init function for PA2. So quick comment on why do we do this instead of just, putting one line in our main program that says, sentinel equals malloc. It's functionally the same, right? In my main program, I could say sentinel equals malloc. I could actually say struct node star sentinel equals malloc, and all of this would be reduced to just, one line in my main program. Why do we put it into a separate function? Basically, yeah, to keep things neater, to keep things organized, so that if we decide to do something different, if we decide we're going to, store our array, you store our linked list in an array of struct nodes, like in PA1, or we're going to use some other library to implement our linked list, right? That library probably comes with an initialize function to create an empty linked list. And if I'm calling my initialize function here, right, I possibly don't have to change this line of code at all when I decide to use a different library. And it's modularization. It's something called information hiding, and it's this general idea of working with abstract data types, right? The more details about creating and working with and dealing with the linked list, the more those details appear in our main program, the more fragile our main program is, right? The more we need to be aware of what's going on, you know, on the other side of the firewall in our main program. And the more work we're going to have to do if something changes in the implementation details of the linked list. And in some cases, you know, you write a main program and it works beautifully, and then the operating system it's running on gets upgraded, and your main program breaks because you were doing very low-level things. For example, maybe we were using code inside main that said, you know, move through the linked list until the next field is equal to -1. And now we move to a different system, and the null pointer value is 0 instead of -1. Well, we got to go and we got to change code in our main program. If those details, you know, what is null equal to, are hidden inside this package of callable functions, right, we just recompile. We download the new library, we say make clean, we say make, and our code continues to work. So we're working on a mindset, basically, you know, it doesn't really make a whole lot of sense for us because we're writing this code, we're probably never going to use it again after Friday. But we're working towards a mindset of, you know, maintainable code that's being used by others, code that's part of a larger project and needs to fit in with other pieces of code, and then possibly, you know, survive changes to operating system or other low-level details. So that's why I tend to do things like this that looks like, well, why not just put that line of code inside main, right? So it's habits. Let's see. Question in chat: how do we get the pointer to actually become the address of the data? If I know what you're asking, right, this is just a pointer. It's just some location in memory. But inside init, right, I might also do something like, you know, s arrow next equals null. And in my main program, Sentinel really is, you know, pointing to a Sentinel node, the beginning of a linked list that says there's no node following me. And then if I want to add something to that, right, I could say add Sentinel 17, and that should put a 17 on the end of my empty linked list. So the memory that was freed up by malloc, that hex address, how would we assign that to a node? So malloc gives us a hex address. You don't really have to assign it. You just start using it as a node. So PA1, right, get node would give us a number like 5, right? And then when we wanted to use that node, we would say, you know, list array bracket 5 dot data equals such and such. And here we get, you know, a number from malloc, which we're saving in a variable s, and we just do s arrow, you know, whatever, to start using that. So let's say we're doing our add function, and we say struct node equals. And, you know, here again I would call get node. But, you know, you can call him Alec. And then I could just say new arrow data equals n. Right, assuming n is one of the arguments to the add function, right? And I'm using it, right? It is kind of a weird concept. But once you have that address, we just decide we're going to use that as a node. We don't really need to like give it to a node or something. It's just how we're going to use it. And that's a really fundamental shift from how we've used variables, you know, in 121 and 224, in 270. This is something different. All right, yeah, play with it and let me know if it's still confusing after you have more code doing that. All right, other questions? Let me take a look at the ODPs. All right, we got some 20s out of 20s, so that's good. Let's take a look at the description. Yeah, so someone mentioned in chat they think they get it. They're thinking of it in a weird way in their head. It's all weird. I mean, and I think I've mentioned before, it took me a number of at least weeks when I first started learning data structures, and linked lists was the first data structure I learned. It took me a number of weeks to really kind of make peace with a mental image of what's going on. And it very much came to fruition through drawing pictures and trying to, you know, stare at a couple of boxes with arrows between them and really find a way to make that mesh with, you know, the ideas of memory addresses and the ideas of the C code. And it was really kind of three different views of the same thing, and it was a struggle. And I think it is for everybody. I don't think it was just me. It was a struggle to sort of connect those different ideas, but once that connection is there, then you're just off and running. You can make all this stuff work. All right, so ODP 207 is a piece of PA2. Or it uses some of the things you're going to develop in PA2, which hopefully you're making good progress on at this point. So you're defining a struct node. Okay, it's the same struct node we're going to see for, you know, the rest of the week. Data piece and the next piece. And make a function which takes two struct nodes and basically connects them together. So basically set the first node's next field to point to the second node. And that's really it. So how would we use this? Define your struct node. You know, declare what a struct node is, and then struct node. You got a few ways to do this. Let's go ahead and do it with dynamic memory. So make your struct nodes. malloc size of struct node, malloc with size of struct node, and then call your link function. Well, let's right, call your link function. Doesn't return anything, but when you get back from here, if you run this inside GDB and you look at first arrow next and you look at second, they should be the same thing, right? First arrow next should be the address of your node called second. Alright. So make your struct node pointers first and second, malloc, call link. If you go in GDB, look at first arrow next, it should be the same as the address of second. If you don't want to do this in GDB, after you malloc, you can do something like second arrow data, give it some value, print first arrow next arrow data. That should show you the current value of second data, right, after you call link. But if you print first arrow next arrow data, you will probably segfault, because before you link together, first arrow next is probably null, right? So try that and then change that to do the print after you call link. And first arrow next should now point to second, and second arrow data should be 25. I think it's easier to look at it in GDB, and I think it's better practice. So cobble together your link program, right, which is again really one line of code, right? Link just takes your first node's next and sets it equal to second. And remember, second is an address. It's a pointer to a struct node. So it's really just first arrow next equals second. So do that, test your link program with a test main, and once it's working, go ahead and compile it with the test bed, ODP 207.0, and then go ahead and assess it. All right, questions on that? So there's a series of ODPs posted this week, and make sure that that you're assessing the correct ODP. So they're listed on Canvas, but your real acid test is when you run the assess command. Right? Look at the part between the asterisks. You are about to assess your code for ODP 207. Link one node to another. Right? If you were reading ahead and you saw ODP 208 and got excited and decided to write your code for that, and you start assessing the code for ODP 208, and you see this message which says you're assessing for 207, don't assess your code. Right? Just use the X command to get out of here. Because if you assess ODP 208 for this and you get a 0, it records a score of 0 for ODP 207. So all of the readmes are available. Right, and I leave those up, and I'm not releasing those in a time-released way, but make sure you're assessing the right code. The test bed for 208 says that it's temp main 20B, not temp ODP. Oh, where is that? Is that in the README? That's fixed. Yeah, I'm trying to be really consistent about the numbering and naming of the readmes and the testbed files. But, you know, human error. All right, cool. Any other questions? We'll talk about 208 when it opens up, which will be tomorrow. And I've set these to close at 10 o'clock and then open the next one at 10:02. So ODP 207 goes until the start of class tomorrow, and then 10:02 the next ODP 208 will open, and we'll talk about that in class. And then 209 on Wednesday. All right, let's talk about the GDB quiz. Open up the quiz. So we started going through these on Friday and we ran out of time, so let me... So I've made a readable file on the server under /temp called G1, and you can just gdb/temp/G1. You can copy it if you want, but you can just gdb it directly from /temp. And this is compiled with symbols, so you can look at source code, and you can see the structure, and you can see some random looking code. So a series of experiments to perform, right? So the first one we talked about already, set a watch point on I. So if you say start and then watch I, it will monitor the value of I, and anytime I changes, it will let you know. So if you say continue, this will run until I is about to change. So the old value was -1, the new value is 0. It's about to do this initialization statement. If I say continue, it will stop down here at the while loop, where the old value of I was 0 and the new value is 1. Right, and that's because at the bottom of my while loop I do an I++. All right, so use continue and step through until I is equal to 5, and then print out the value of X. Type that answer in here. How many bytes are allocated for the structure myStruct? Go ahead and use, it tells you what its new value is actually. So watch points kick in after the value changes. So for example, it said old value is 1, old value is 0, new value is 1. And when I print out I, it's actually equal to 1. If I say continue, it will stop up here after I has changed. So now I is equal to 2. Breakpoints stop before it executes the line that the breakpoint is set on, but watch points fire after the watched variable has changed. All right, how many bytes allocated for the struct myStruct? Just print the size of struct myStruct. You can do that from GDB. What's the starting address of the array name data? I changed the wording on this a little to try to make it clearer. So data is a pointer to a struct myStruct. It's an array of myStructs. And so DATA, right, is an address. When you have the name of an array in C, it's actually referring to the address where the array begins. So figure out what that address is. And I'm not asking you to do like double indirection or anything here. Just when you call a function and you give it an argument of data, what's the value that's passed to the function? And then what's the address of data bracket 0? Well, you can do that in GDB by printing ampersand data bracket 0. And you should find that it's the same thing as, you know, what you put in question 3. What's the address of data bracket 1? Well, it will be the same as the address of data bracket 0 plus some kind of offset. How much of an offset? Well, should be the size of whatever your mystruct is, which is what you found in question 2. So as you're doing this, you can be building a memory map. And you're going to find that at some location, which is data, we have the first byte, the first bytes of data bracket 0. And that'll occupy some chunk of memory. The size of it is what you got from size of struct, mystruct. And this is followed by data bracket 1 all the way down to data bracket 9. So if you print the address of data bracket 1, you should get some number here. If you print the address of data bracket 0, you'll get some number here. And they'll separate by the amount of space allocated for the struct. An array basically packs your data in as tightly as possible, given the size of the thing that you're putting in each element of the array. In this case, a mystruct. Now, a mystruct has space in it because it's got all these different fields in it. It's got some characters, an integer, another character, a double, and another int. All right, so look at the addresses of these and then hypothesize a formula for the ith element of the array. And it'll be one of these. All right, now we want to dig into the mystruct itself. Contains several fields, right, characters and so on and so forth. Figure out which one is stored first. And the way you do this is by print the address of, for example, data bracket 0.x. Print the address of data bracket 0.c1. Print the address of data bracket 0.z, right? And build yourself a memory map of what a mystruct looks like. So this is just an example. So you might find, for example, that you know, x begins here at locations 0 through 3, and at locations 4 through 7 we find y, and then at location 8 we find character C1, at location 9 we find C2, and at location 10 we find F1, at location 11 is unused, and then maybe locations 12 through 15 we find the double F, and so on. Yeah, sharing internet access is tricky. All right, so you're building a memory map, right? And this is something you want to be able to think about as you're working with dynamic memory. So I didn't have my page up. Here's a mystruct, right? So x might be stored in these locations, and y here, and then maybe a character in this byte, and a character in this byte, and there's going to be some spaces in there, and so on. This is not what you're going to find, okay? But you want to look for something, you know, like this, but the true version of it, by basically printing the address of these different fields. So for example, this, you know, I could find by printing the address of data bracket 0.x. And if I want to know where y begins, I could print the address of data bracket 0.y, and so on. All right, so that will let you figure out which field is stored first. And then look at the size of each of these fields, right? So you know, this is a character. You can print the size of data bracket 0.c1, c2, y, f1, and so on. Figure out what the number of bytes are that are required to store each of these pieces of your structure. Add those up. And you'll find something smaller than the total amount of space that's allocated for a MyStruct. So what's the expected number of bytes required for storing the complete set of fields? Since your answer is less than 32, which is the size of a MyStruct, there's some unused space. Somewhere there are, you know, one or more gaps in this structure that have been set up by the compiler for field alignment. So find the address of the first gap for data bracket 0. So you're going to need to have a memory map. You're going to need to fill in specific addresses here for data bracket 0. And if this is the first gap, then your answer to question 10 is the address where this gap begins. And this will all be, you know, not too long, but kind of long hexadecimal numbers that you're getting from interacting with GDB. So unless you've done this kind of thing before, this is not something that you're gonna rip through in 5 minutes, right? So don't, you know, start it 5 minutes before it's due. Okay, it's fundamentally different from the other quizzes, which are largely just kind of, you know, touchstones like, you know, do I know what a linked list is? Do I know what a sentinel node is? And so on. This one actually requires you to get in there and do some work. But it's work that you'll end up doing, you know, again and again as you develop code and such. All right, so any questions about that? I don't think there's a time limit on the quiz. I started mine a few days ago and it's still letting me go. So I think it's set up to have no time limit and to let you do it as many times as you like. No time limit, multiple attempts, keep the highest score. Number of attempts unlimited, view responses. Alright, and we looked at quiz 1 already. Let's take a look at the other ones. Do it till you get it right. Alright, so we looked at this one already. The one we didn't get to was quiz 3. Alright, so quiz 3, linked list quiz, right? And we've been doing linked lists for a while, so you should have everything you need. Which of the following is true about memory and linked lists? A sentinel node in a linked list is one of these. A linked list is like an array, is like an array, is like an array, is nothing like an array. Thinking about PA1, abstract data types. as an abstract data type, which is not supported. So, so work through that quiz and let me know if you have questions. But I think we've got enough linked lists down to cover all of that. And then the other quizzes come a little later. You can take these anytime that you want. But this one is, I believe, stacks and queues. Oh, this one is hashes. Wow. A one question quiz. No. Wrong one. Preview. Alright, so that one's on hashes. Alright, good on that. Alright, let me just talk a little bit about variations on linked lists. And these are not things you want to do for PA2, but in general, there's more to linked lists than what we're doing so far. One of the nicest variations is to make what's called a doubly linked list. So our linked list normally looks like this. We have nodes pointing to the node that comes after them. Doubly linked list, you simply include another pointer in each node which points backwards one spot. Takes a little more memory, right? You've got one more field in your node declaration to have this back pointer, but it potentially simplifies your code a lot. For example, when you want to delete a node, so let's say this is 4 and 10 and 17 and 32, and we want to delete 17. Well, we don't need that pair of pointers anymore, right? We simply start here with a current node. That's not what we want to delete. Change current to current next. That's not what we want to delete. Change current to current next. There's the node we want to delete. Well, now we know what the previous node is because we have a previous field here. And so to remove this node, we could say something like current previous next equals current next. And that one line deletes your node. So your nodes look like this. And this says take the current node, follow it to the previous node, that's this block, take that thing's next field, that's this block, and set that equal to whatever current next is. And then you also need to adjust, so that changes this to point to that. And then you need to change the back pointer on the next node. So you'd say current next previous equals current previous. So take the current code, follow it to the next node, take its previous field, which is this, set that equal to whatever the current node's previous is. That does that. So a little more memory, a little more work every time that you manipulate the structure because you have a pair of pointers to keep in sync. But we can move in both directions now in the list. So when we're inserting or we're deleting, we can back up one spot. If you had a lot of data stored in a list that potentially had locality of reference, you could move through a list. Let's say it was alphabetized, and you knew that references were always made near the previous reference, right? We could keep our pointer to where the last reference was, and then when the next request comes in, right, if it came before the one that we just made, we could start backing up. And if it's going to be close to where the previous request was, right, we might have to do less movement through the list than if we always started from the beginning, or always started from the end. So in some cases, this can make things more efficient. And you can do this with or without a sentinel node, right? If you have a sentinel, then your sentinel points to the first node, and your first node points back to the sentinel. Or you could set you could do a linked list without a sentinel. And I want to talk about that. We're just about out of time. I want to talk about a linked list without sentinels, and I want to touch on circular linked lists. And then we're going to move on to our next structure. And I think we're going to go through stacks and queues next. And then hashes at some point, but then we're going to head into trees. And that's going to be the really fun and intense part of the course, is talking about binary trees. Alright, we are out of time officially, so I will see you next time. Work on the ODPs, work on PA2, bring questions. Thanks.